Okay, now that we've done an example of the span of two vectors and solving linear combinations, I want to think a little more generally. So, so what are all the possibilities? If we just take two vectors in the plane, you know, I'm saying here, these two vectors are in R2, then what are all the possible results of the span of those two vectors? Okay, so let's just talk about the first case, which is, and let's use this example that we used in the last video, with V1 being 3, 1, V2 being 4, -3. And the thing that we saw is that if you try to solve x1 v1 plus x2 v2, and I'm actually going to call this thing of equal sign y, because that's kind of a variable too now. It's like we want that to be any vector possible, right? So that really becomes, if we sort of change that into equations, right, then you get something like x1 times 3, 1 plus x2 times 4, -3. Let's actually call this y1, y2. And, you know, maybe I'll skip a couple steps and just say basically you end up with the system of equations, or the augmented matrix, sorry. First column 3, 1, second column 4, -3, and then this variable column. And again, we call, you know, it's sort of noticing that this is, the first column is V1, the second column is V2, and the third column is this Y. If we row reduce this, well, we saw this with the example that we did, that in fact, it row reduces to that nicest possible form where you have two pivots. That's not a 6, that's a 0. And, you know, I could just put asterisks here to say it doesn't, because it doesn't really matter. I'm just kind of proving the point that this is consistent. Right, pivot in both rows. Pivot here, both consistent. So, so we can solve this no matter what y1 and y2 are. So it's really consistent for all possible choices of y1 and y2. And that means that every vector in R2 is a linear combination of V1 and V2. This is, you know, we sort of saw this geometrically in the last video, but now we sort of have an argument, right? So like, i.e., every vector, every possible y vector in 2D is a linear combination of V1 and V2. And that just means that thus the span of V1 and V2 is all of R2. And okay, so that means, so the span could be all the entire plane, right? Basically, we can generate every vector can be generated from V1 and V2 just by scaling and adding. And what's the key point here? Geometrically, this will work whenever V1 and V2, as long as V1 and V2 don't point in the same direction, right? Because that's how we get that grid that we saw in the last picture. And that should work fine. So geometrically, this will work for any, this will work for any V1 and V2, which I'll just put this in quotes, point in different directions. So you have something like, you have something like, just draw some axes here. Draw better axes. And if I just pick two vectors, you know, if I've got one going this way and one going that way or something like that, and I have v1 and v2, then, you know, you can sort of make this sort of grid, the grid lines out of that, I think, right? You can sort of say like, oh, there's some grid lines here. That was supposed to be parallel to v1. Let me see if I can do that better. You know, you kind of make your little grid. Then you also have the grid parallel to v2 and so on. And it feels like every point can be reached by scaling and adding v1 and v2. Okay. So that's one case, but let's do a different case now. So second case, let me just do an example again. Let's say v1 is the vector 3, 1, and v2 is the vector -6, -2. Okay, now if we make our augmented matrix, I'm just going to skip all the previous steps because I think you get the idea now. With a generic y1 and y2, what's going to happen? Well, it's going to row reduce, and you're going to get 1, 0, -2, 0, right? You're going to get a row of zeros. This is actually going to be y2 because the first thing was to switch row 1 and row 2. And then this is going to be y1 -3y2, I think. And so this will only be consistent if y1 equals 3y2, right? This is only consistent. It's only consistent if this is 0 right here, right? So it's only consistent if y1 equals 3y2. And in fact, you can think about what that means now geometrically. And what the point, you can sort of see how I chose v2 from v1, right? Let me draw something over here again. So now we have our vectors, and here is 3, 1 is, say, like that. Actually, let me make it a little shorter. So that's v1, and v2 is actually twice as long in the opposite direction, right? v2, and now you have that problem. You can sort of see, I can't escape this line right here. Every vector, if I combine v1 and v2 just by scaling and adding, there's no way to escape this line. And in fact, if you really want to do, maybe, is think about this as the, this is sort of the y1 axis, and this is the y2 axis. That's kind of strange, but if you think about it, that's what putting y1 and y2 right here is. This is like the x and y coordinates of the point. Then you could also write this line as, maybe, if we want to think about like y equals mx, it's really y2 equals 1/3 y1, and that's exactly what this line is. It's the line of slope. This is the line y2 equals 1/3 y1. It's the line of slope 1/3 through the origin. Right? And so now that tells you that span is just a line through the origin in this case. So here, the span of v1 and v2 is a line through the origin, containing both of the vectors. Okay, so yeah, so in the first case, I'm going to do a couple more cases, but in the first case, I just want to point out, this was the matrix that we got, the reduced echelon form, the 1, 0, 0, 1, which is our nicest. It's actually called the identity matrix. And then down here, we got a matrix of the form, maybe I'll put it over here. The matrix is of the form, you know, it just has one pivot is the point. That's like that matrix. Up here, this was the 1, 0, 0, 1. Oh my God, I just left. Sorry. So this is called the identity. This is 1, 0, 0, 1, and this is called the identity matrix. We'll see why it's called that later. So we had this case where right here, and I'm just kind of thinking about all the possible reduced echelon forms, because that's what this comes down to, if you think about it. So let me think about what else we could have. So, or in fact, maybe even before I write 3, let's just say other reduced echelon forms. And I can sort of think of 2 more. But now we have to start considering the 0 vector, because, you know, 0 columns in systems linear equations don't make much sense, because you're basically saying a variable is not involved. The 0 vector can show up in certain situations, and it's sort of worth mentioning. So here's another reduced echelon form we could have. We could have something like this, right? I guess in the second example back up here, this asterisk could be a 0. So that would be the second column being 0. It's maybe worth thinking about. But here, so this could come from something like the following. You could just basically have v1 is the 0 vector, and v2 is anything non-zero, right? Anything non-zero. And that would reduce to this. That would reduce to this. And that sort of tells you that now the span, well, what is the span? The span is really just, it's still just the line. It's basically multiples of v2. So the span of v1 and v2 here is a set of multiples of v2, because the 0 vector doesn't contribute anything. And this is, again, a line through the origin. So that actually isn't different from the previous case, which makes sense. That it shouldn't really matter if the first column is 0. We said this, that we sort of already see it up here, the possibility of a 0 column with the asterisk being 0. So it really shouldn't matter if I switch over to the columns. That should be pretty much the same thing. So kind of, this really is kind of the same as 2. I guess I should say same as possibility 2. It's just the 0 vector could have been one of the vectors. And then the fourth case is that you could have just v1. The fourth sort of reduced echelon form, which is a really kind of dumb one, is just this matrix of all zeros. So like v1 equals the 0 vector and v2 equals the 0 vector. And then what's the span in that case? What are all linear combinations of the 0 vector and the 0 vector? Pause if you are not sure. It's just the 0 vector. You can't create anything else. So now the span is literally just a point. So that's what we get. Okay, so those are all the possibilities for a span, and it's worth thinking about. It's either a point, what really is just the origin. So maybe I should write this out. The possibilities then, sort of from least interesting to most interesting, for span of 2 vectors in 2D is you can either get just the origin, a line through the origin. I claim any line through the origin. You could sort of check me. Basically, if the 2 vectors are on the same line. So it even could be a vertical line if both vectors didn't have an x component, say, right? Or all of R2. And there you go. And this is going to be something we're going to see as you go up higher dimensions, that the origin is really important, that you can always get 0 as a linear combination, because you can always just have, scale them by a factor of 0 and kill both vectors. And we get something linear. We don't get like a curve through the origin. We get a line through the origin or the whole space. And so that is another reason why all this stuff is considered quote unquote linear. And And when we go up dimensions, you might be able to guess what happens when you go to maybe 3 vectors in 3 dimensions. But I will do that in the next video, so I will stop there.